about data with two sets of samples, right? And we were doing that yesterday, but what was special about the data we were looking at yesterday? It wasn't just two totally random sets of data, it was matched pairs. And so because that data was related somehow, we basically just had one extra step. We had to find the difference between the groups, and then we did all of our normal stuff with it. When we're talking about a mean, we do the t-test and work from there. Today we're talking about what do you do if you have two totally different samples. So they are independent, they are not related, so we can't just put them together and find the difference between them. The calculation for this t-value is a little complex. We know t is kind of like a z-score, so it's always r value minus the mean divided by standard deviation. Well, all of a sudden, you have two different sample means, two different sample standard deviations, two different population means, and possibly two different numbers in the samples, because we just have totally different sets. And so the t calculation gets really ugly. It's the sample mean of one set minus the sample mean of the other. Okay, there's one. Minus population mean of one minus population mean of the other. Divided by the square root of our standard deviations divided by n for each group. So that one, pretty sure is on our formula sheet, should be under chapter 11. Yep, it's the second column on chapter 11, the first bullet. That is the test statistic, if we have two totally different samples. And that's kind of why with matched pairs, we want to put them together and make one group, so it's a lot easier to work with. Degrees of freedom on this, I should mention. Because the two samples can be different sizes, we know degrees of freedom is just the number in the sample minus 1. So if you're looking at two different sets, you do the smaller one. Okay, so if one was a sample of 20 and the other was 17, we would go with 16 degrees of freedom. So we base it off the smaller set. So our criteria, we have to know the means of the original populations, so we can do it. Has to be simple random sampling, independent, both populations have to be normally distributed, or both samples have to be bigger than 30, and can't exceed 5% of the total population. So all the same stuff, except now it's either they're both normal or they're both bigger than 30, because we have two different sets. So our hypothesis testing now, we're not looking at the difference, so we're comparing the means. So it's the mean of the first equals the mean of the second is the null, always. Then the alternative can be they are not equal, less than, or greater than. So we still have left-tailed, right-tailed, two-tailed. Just the null and alternative is a little bit different from yesterday. We have to have an alpha level, then we compute our t. And so then we know either classical or p-value approach. Classical, you're comparing your t alpha with the t you calculate. So our t alpha gives us like a shaded region, and if the t we calculate is in that region, we reject. P-value approach is we find our t, get the probability of that, and then when do we reject? If t is less than alpha. All right. Just talked about that. So let's look at a problem. All right, a researcher wants to know whether state quarters had a weight that was more than traditional quarters. He randomly selected 18 state quarters and 16 traditional quarters, weighed each of them, and obtained the following data. Test the claim that state quarters have a mean weight that is more than the traditional quarters at the alpha equals 0.05 level. Assume the data is normal. All right, first of all, is there any way this could be matched pairs data? No, I don't even have, for matched pairs, they have to be the same number in both sets, first of all. So that's a big red flag. But also, I just took a random state quarter and a random traditional quarter. It wasn't like they were minted in the same location on the same day or anything. There is no reason to link those together. So we have two totally different sets here. We need to start by entering these in our calculator. Let's do the state in L1 and the traditional in L2. So double check, we should have 18 in the first, 17 or 16 in the second. Now, how we do it depends on our first. So first I'm going to walk you through how we would do it by hand, and then I'll show you how to do it on the calculator. Okay, I think, did I leave some blank slides after this?
Yeah.
Okay. So if we're going to do this by hand, we need some information about both of these. We're going to have for each set, we would need the mean, the standard deviation, and the number. I already know the number in the first is 18, the number in the second is 16. But then we would use our calculator to find that information. So we go to stat, calculate. You can either do one variable statistics for each list separately, or if you want them both to show up at the same time, you could do two variable statistics. Let's make our X list L1, Y list L2, make sure the frequency is empty. And it's going to tell us error. Do you know why? Because they're different sizes. When you do this, even though it will show up as the mean of the X and the mean of the Y, it's trying to treat them as ordered pairs. So on this problems where both sets are the same size, you could go into that and get it to give you both on one screen. Otherwise, we're going to have to go through and do them separately. So if we quit here and go to stat, calculate, we'll have to do one variable statistics because our sizes don't match. Let's do with one first. And the mean is 5.7022.
Thank you, sir. Sorry, it gets a little loud.
Standard deviation 0.0497. And then we need the same thing for the second list. So we go to stat, calculate one variable statistics, but now switch it to L2. The mean, we get 5.6494. Standard deviation 0.0689. All right, so then we would have to have the T statistic. So it's that complex formula that was on our first slide, or you can look on your formula sheet under chapter 11. Oh, what did I never write down though? The null and alternative, yeah. I don't have to worry about the criteria because I did tell you it was normal, but we definitely need that if we're going to the null and alternative. The null would be what? The alternative, what am I trying to test? If the state quarters have a weight that is more. So if the first is more than the second. This is also why it's important to use the first one for L1, the second one for L2. If you flip them, it will switch this. When we're looking at our hypotheses, if this one's bigger than when we should subtract them, should we get a positive or a negative number? Positive. When we were doing that yesterday, when we were always doing 0 on the other side, so that meant greater than would mean the first was positive. Okay. So, to get our T, it's the mean of the first minus the mean of the second minus, okay, the population mean of the first and the population mean of the second. Did I give you those? No. But my null hypothesis, we assume that's true unless we prove otherwise, right? If the null hypothesis is true, those population means are equal. So what would you get when you subtracted them? 0. Over square root. Standard deviation of the first one squared divided by the n of the first plus standard deviation of the second one squared divided by standard deviation of the second. All right. Do we get 2.54? Yes.
I did not get that.
Okay.
Your square root ended after the first one. It needs to continue. Oh, okay, you're welcome.
I think that's what mine did too.
Did it?
Yeah, I haven't measured it.
Yeah, it's got a little bit of that hole.
So,
Square root. You're welcome.
did you get it?
Well, I have to retype it.
Retype it. Okay. All right. Anyone else have a calculator problem there? All right. From here, we have two different options if we're doing it by hand, classical or p-value. So I'm showing you both because I've just kind of noticed that some of you prefer different things. So on this, I'm not going to ask you to show me both methods. It's just kind of whatever makes the most sense to you. Classical approach requires us to find what? What do I have to compare it to? The shaded region. Okay. So we would need our cutoff value, our T alpha. This is not a two-sided test, so that helps a little bit. So our alpha, we were looking at 0.05. We're testing greater than. So we basically are looking at, okay, what is the T so that 0.05 is to the right? How many degrees of freedom do we have on this problem? 15, because the sets are different sizes, you have to base off the smaller one. So 16 minus 1 is 15. So if we go to our T distribution, Okay, 15 degrees of freedom, 0.05, then the t statistic is 1 point. Okay. Would 2.53 be in the shaded region? So if it's in the shaded region, we the p-value approach is finding this probability. So if we have 15 degrees of freedom and the t is 2.53, so that means you're going over and finding the closest number in this table you can get to 2.53. And the closest is what? 2.602. Does everyone see that? So if you go up, the probability of that is 0.01. Alpha was 0.05, so since p is less than alpha, we reject the null hypothesis. Are there questions on how we did this by hand? Now, by hand is really not going to be our preferred method here. We're already putting everything in the calculator to get this stuff. So if all of our information has already been entered in the calculator, it really makes sense to continue to do the problem on the calculator. So that's really what we're going to do. You can do it by hand if you really like to and you're opposed to the calculator, but our calculator is preferred. All right. So on our calculator, we have everything entered into our L1 and L2. We are going to go into stat, tests, and we normally do a t-test, but now we have 2 samples. So we're going to do the 2 sample t-test. Stat, test, 2 sample t-test is number 4. All right. So then you can tell it if it's based off data or stats. Stats would be if the original problem just gave you this information and then you enter it in. And so we've already written it down. We could certainly do that, but it would be easiest. We already have our data entered, so we could just say data. You have to tell it what list. So list 1 is L1, list 2 is L2. Frequencies need to both be 1. What was our alternative? Greater than. Pooled, just keep that set as a no. Okay, so pooled should always say no and calculate. If we do that, the 2 things that I ask you to write down are your T and your P. So we get our T to be 2.5366, pretty close to what we had, slightly different because we rounded, of course. The P 0.0086, we had 0.01, so again, not horrible. Then we just look, since P is less than alpha, we reject. If I ask you to write a sentence, what does that mean to reject the null hypothesis? what were we trying to conclude? That state quarters weigh more than traditional quarters? So I showed you all the ways of doing this. What I really expect for you guys is to do it on the calculator. So you can do it by hand certainly if you'd like to, but most of them from here on out will just rely on our calculator to do. Any questions there? The other option we have with hypothesis testing is to do the confidence interval. So we could be asked to do that. The confidence interval, again, because we have two separate means, it becomes more complicated. We're used to doing like x bar plus or minus the t times the square root. Well, it's similar, but since we don't have only one x bar, we have to subtract the two for our standard deviation. We have to add them together. Degrees of freedom is still based off the smaller. So if we looked at this problem, construct a 95% confidence interval about the difference between the population mean of a state quarter versus the population mean of a traditional quarter. So I'll walk you through by hand and then I'll show you on the calculator. All right, we need our t value. It's like alpha over 2. We want 95% of the data to be in the middle. So we have 5% to split. Yeah. All right, so if 95% is in the middle, we have 5% left over. So that means 0.025 on each end. How many degrees of freedom are we basing this off of? 15. So we go to our table. 15 degrees of freedom, 0.025 for the probability, and 2.131. So, formula, mean of the first minus mean of the second. So we have those written down here. 5.7022 minus 5.6494. And then we do plus and minus the t alpha over 2, which was 2.131, times the square root, and we normally just have one standard deviation, but here we have two. So the first squared over the n for the first, plus the second over the n for the second. So what this means, we are 95% confident. What? What do these numbers represent? Yeah. The weight difference is between these numbers. So they're both positive, so we're basically saying state one's way more. Okay, this is all based on the difference, the first minus the second. We are 95% confident. weight difference. And we did state minus traditional, L1 minus L2. Is between 0.0084 and 0.0972. So then would this tell me reject or fail to reject? Reject. Why?
Because it's proving that equation.
We look, our null hypothesis was that they were equal. If they're equal, then the difference between them should be 0. 0 is not in our interval. So we reject the null. All right. So that's how to do it by hand. Again, all from the formula sheet, just plugging numbers into a formula. We can also do it on the calculator. And again, this is going to be the preferred way. We go to Stat, Tests, to Sample, T interval. Okay, so it's taking the normal things we do, the t-test and the t-interval, and we're just doing the two-sample t-test, two-sample t-interval. So that was, I think, 0 maybe, stat, tests, 0. Okay, we're basing it off data. If you had to do stats, so you know what it would look like, you would have to enter the mean, standard deviation, and number for both of them. So nothing too crazy. Data, just make sure list 1 is L1, list 2 is L2. Frequencies are both 1. What was our confidence interval? Pooled, just keep that as no always. And then calculate. Okay, so then we get our interval slightly different. 0.0101 to 0.0956, but still very close to what we had. And again, since our null hypothesis that they are equal, 0 is not in there, so we would reject. Do you guys have questions? All right. So we will have a day Monday to work on finishing this homework, and I will probably, we're going to do another practice assignment over chapter 11 outside of this packet. So if people get done Monday, I might give it Monday, otherwise I'll give it on Tuesday, just additional practice. Like I said, unless it specifically says do it by hand, you're welcome to do the calculus.